Hi, this is going to be the second part of the section 5.3 material that we need to cover. I'm going to be sharing my slides. Okay, so we're going to be talking about hypothesis testing a little bit more today. We have some different types of hypotheses that we need to think about in a large group setting. I guess what I really mean by that is a kind of categories of types of hypothesis testing. So the one that is covered in the book is the single group. And this is the one we already started talking about. So this is where we talked about the value of a parameter. It's either a mu or a p, a proportion or a sample or a population mean or a population proportion. And we want to know if it's not equal to or less than or greater than some value. So this is where we talk about the mean of a large sample, where n is greater than or equal to 30, the mean of a small sample, where n is less than 30, or a proportion. And then there's two sample groups, or two samples, or two groups within one sample. There's a lot of different ways where you get two groups that you're going to get either samples or proportions for. And what you really want to do, and this is really the more useful types of hypothesis testing, you have to learn how to do the single group ones to really understand the math and statistics that go into the do the two groups. But the two groups are the ones you really use more, because you really are asking, is there a difference between the means in two groups, or is there a difference in the proportions between two groups? And that's really often the more interesting question, or what you really want to know. So we're going to look at how to do 4 different types of tests that fit into this larger category. We're going to look at how to do the difference between two means when you have a large independent samples. We're going to look at how to do the difference between two means when you have small independent samples, and the difference between two proportions. And then we're going to look at the difference between two dependent means. Now, I have been informed, so I hope it's accurate for you, that most of this material was covered in 210. So I'm going to be going a lot faster than I would if I felt like this was the first time you've seen this. If you feel shaky on it, or you need to slow down, please come to my office hours, set up time with me. There's no, I don't think less of you. I think more of you. If you really want to make sure you know the stuff from 210 that you were supposed to have come into this course with, if you feel like you needed me to help you review it at a slower pace. I am trying to put most of what you need in the notes. I'm just going to go through them quickly. Okay, then we're going to talk about some stuff that I think will be new. It's not covered in 210 to my knowledge, at URI anyway. And that's when you're comparing multiple, by multiple I mean more than 3 or more than 2 proportions. And so the idea is that you would get the same type of proportion, like, what proportion of males are former smokers, or what proportion of females are former smokers. So the proportion is the same thing, whether you're a former smoker. But the groups are made up by a categorical variable, for example, where you would divide males or females. So this type of testing is where you have 2 categorical variables, and you want to say things about the different proportions in each one of the categories. So contingency tables are involved with this, and we'll see how to do that. So again, one categorical variable leads to different groups. The second categorical variable would be used to create the same proportion from each group. So we'll see more of that later. And then also we're going to learn about comparing multiple means. And again, these are sample means. So we want to say something about the groups that they come from, and something about the population mean in those groups. And to do that, we are not going to be able to just use the previous approaches that we were doing. We're going to learn something called ANOVA to handle that. And that is, these are numerical variables, right? So we are going to get sample means. Okay, the first two big categories, the single group and the two group, have a very similar type of approach for all 7 of these tests. And that pattern for these tests are, first, you want to understand the alpha, so the probability of a type 1 error for your specific hypothesis. Sometimes it's a one-tailed test, sometimes it's a two-tailed test. You have to think about where the alpha goes and how to think about it when you use it to do your test. And then in all of these, we're going to have this general structure where we have a test statistic that is a calculation that is obtained using the observed value or values minus the expected value or values over a standard error. And what is actually going into each one of those components varies depending on what exactly, so here we have the observed value, expected value. These are, think of these as like Tupperware boxes, and we're going to put stuff in them depending on which of these 7 types of tests we're going to do. Then we want to, once we have this test statistic, so the whole goal is to get to this test statistic initially. That's the first thing. And then we're going to determine the probability of seeing that result if the null hypothesis is true. And from that determination, and that's a probability when we calculate, that is what we call the p-value. So the probability is the p-value, and some people call it the significance of the test. And that is actually the more sophisticated way to talk about it, is to say it's the significance of the test. Although you really hear a lot of people talk about p-value. And we use that to determine if we believe, given the significance, which is, remember, how much risk we're willing to take to be wrong, whether or not we believe that we can reject the null hypothesis or not reject the null hypothesis. And then we always want to summarize the results back to English. So just wanted to make sure that we are clear that the observed values you calculate from the sample, and that the expected values come from your hypothesis, and they're proposed. So let's talk about this first group, where you have a single group and you're trying to determine if the population parameter, what the relationship is to some number. And what that number is can come from, really large internet studies, or studies that have been published that claim what the population parameter is. They can come from actually knowing what the population parameter is, or they can just come from a claim of sorts. So again, the general structure is the same: observed value minus expected value over standard error. And we're going to talk about the first 3 basic kinds. And this is where we have a mean. We want to look at the mean of a large sample. And by large sample, we mean that the sample size is greater than or equal to 30. For that, we're going to use a standard normal, where we have, you may recognize that the standard error is the same as we did for the confidence intervals. It's the sample standard deviation divided by the square root of n, the standard error. And we use a standard normal distribution to do this test. Then we have a situation where the mean, we're looking at a mean from a small sample. The sample size is less than 30. And here we're going to use a student's t distribution. And so we need a test statistic. And it's the test statistic, we give it the notation little t. Sometimes we put a little t with a little df, or degrees of freedom, because we also need to always know the degrees of freedom when we're talking about a t statistic. So it has the exact same calculation as the one for the standard normal above it. The only difference is that now when we go to get the probability, we're not going to look at the normal distribution, we're looking at the t-distribution with the degrees of freedom n-1. And then the last one that is also very similar to what we did with the confidence intervals is we're going to look at the proportions. So here we are going to require that we have, to be able to use the standard normal, we have to be sure that the normality assumptions can hold. So to do that, we want to make sure that n times p, and we're going to use the sample p because we don't really know what p is, the population proportion we may not know. So we're going to use the p bar, the sample p. But the idea is that np is greater than or equal to 5 and that n times 1 minus p is also greater than or equal to 5. Then if that holds, as you notice, we have the observed value minus the expected value in the numerator. And then in the denominator, we're going to have a standard error. And this is the same standard error that we've been working with in section 5.2. And again, we're going to look at the probabilities that come from the standard normal distribution. Okay, so let's look at this steps in doing this. We're going to get this test statistic, and then we want to determine the probability of seeing that result if the null hypothesis were actually true. And that probability is what we call the p-value, and we use the p-value compared to the alpha. So let's look at this in the different types of hypothesis that you could be setting up. So you could be saying that your mean is equal to some value mu naught, and then the alternative is that it's not equal to that. In that case, we have some risk that we could be wrong that we're willing to accept, and we put it out in the tail. So we split it in half and put it out in each tail. Then we have the situation where instead we are just going to make a claim that we want to show, or hope to show, or argue with our data that the mean is actually greater than some value. So mu naught, remember, just means some number. So the null is that that's not true. So it's that it's less than or equal to that value. And in this case, we call this a right tail test because we, where we are going to be putting the risk of being wrong, and where we're going to be trying to look at the probabilities of where our data, how likely our data is possible given our, if our null is actually true, is out in the upper part of the tail. So we're going to put all of our alpha risk a probability. Remember, alpha is a probability of a type 1 error. So we're going to put all that up in the upper side of the tail. And then we're going to put the, in the lower side of the tail, we're going to put, whenever we do it the other way, where we actually want to try to show that the population mean is less than some value. So we're going to have our risk of being wrong, of making a type 1 error where we reject the null when actually it's true. We're going to put that probability in the lower end of the distribution, or what we call the left tail test. So when we calculate the test statistic using this standard structure, the observed value minus the expected value over the standard error, we're going to get values for the test statistic. And they're going to either be above or below the expected value. You know, maybe you'll get one right on it, but rarely. And what we want to do is then look at the probability associated with the tail starting at that test statistic. So if we look at the one, the first one where we put alpha on either end, in this example, I'm just showing where the test statistic would either be on the left or right. It won't be both. It's going to be one or the other. And the idea is once you determine if it's above or below where your expected value is, then you're going to get your probability for the tail. So if your test statistic number comes out greater than the greater than 0, so it's a positive, then you're going to do lower tail equals false when you get this probability, because you want the upper tail. But if the test statistic is below the expected value, so that when you do the, the observed value is below the expected value, so the test statistic would be negative, then you're going to get the probability in the left end of the probability distribution, or the left tail. Okay. If the value at the p-value, right? So in these cases, and over here in the middle, we're looking at the right-tailed situation, and in the far right column, we're looking at the left tail. And all of these, I've shown situations where the probability, remember the area under the curve, is the p-value. So it's the probability associated with a value of the test statistic that we observed, or something more extreme. And so we want to get all the cumulative probability out here in the tails. And then what we're going to say is, well, if that probability is greater than our alpha, which is our risk of being wrong, then that means we're taking too much risk. What we're seeing is likely to be seen given the null hypothesis. So therefore, we do not reject the null. And actually, it's more statistically significant to say that, it's more sophisticated to say it's not statistically significant. So that's usually how people would refer to that. Although some people will say we don't reject the null. Sort of the translation as a consultant, remember you're a consulting company here, to what is slightly less statistical jargon is to say it's not statistically significant. And that's sort of, it means something very specific to statisticians, but people who are not statisticians understand it as well. Okay, so the case where the test statistic is more out in the tails of the distribution, we have the situation where we are able to possibly have a probability or an area under that curve out there in the tail starting at the test statistic that has less probability than the alpha, remember, which is our probability of risk. And if it's two-sided, we're going to put half of alpha on either end again. And in these graphs, what I'm showing is a situation where we can reject the null. So we say that our test is statistically significant. Okay, so now let's talk about examples of each one of these. Oops. All right, so a researcher claims that the average wind speed in a certain city is 8 miles per hour. A sample of 32 days has an average wind speed of 8.2 miles per hour and a standard deviation of 0.6 miles per hour. At a significance of 0.05, is there enough evidence to reject the claim that the researcher believes that the average wind speed in the city is actually 8 miles per hour? So this is going to be a two-tailed test, because what the alternative is, or what we're arguing, we're sort of arguing against the researcher, is we're saying, okay, well, we have this data and we're going to see if the data supports that that's not true. So it's going to be a two-tailed test, because we don't really, so sometimes you can choose, if you kind of know which direction it's going to go, you would choose one-tail test because you have a better chance of rejecting the null. But if you're just making a general claim that it's not equal to you, that's a two-tailed test. And here we're going to split the alpha on each tail of the normal distribution. Okay, so the first thing we always do is set up the hypothesis. And then the second thing is we're going to use the sample data to calculate the test statistic. And this is where I'm going to start to go a little faster. The notes will all be on Brightspace, but if you need me to slow down, you need to come see me. So we're going to get the standard normal using the standard normal calculation for the z-score. And then using that z-score, we're going to figure out if the probability associated with that 1.89 is greater than our alpha. So this is a two-tailed test, and the 8.2 is greater than 8. So once you do a two-tailed test, you have to look at the sign of the z-score, if it's positive or negative, or if your sample data is greater, your observed data is greater than your expected data, to decide whether you're going to use the upper tail or the lower tail probability. So in this case, we're going to use the upper tail. So we're going to use that p norm, the 1.89 with the lower tail equals false, and I get the 0.0294. Now, 0.0294 is more probability of this occurring than our significance level, which was 0.025. So we cannot reject the null. That means the test is not statistically significant. And in summary, the data does not support the alternative claim that the wind speed is not 8 miles per hour. Now, we haven't necessarily proved, we just said that the data is not significant to show it is not. So we don't claim that the researchers' claim is true, and that's an important distinction to understand. Okay, suppose here's another example, and here we're going to be talking about a single mean with a small sample. So here we're going to be doing the student's t-distribution. Suppose a hiring manager wants to establish that the mean retirement age is greater than 67. So in other words, the manager wants to make this claim that the mu, the population mean, is greater than 67. And consider a random sample of 25 retirees that have an average retirement age of 71 with a standard deviation of 9. Does this provide sufficient evidence to reject the null hypothesis that the retirement age is no more than 67 years old at a 5% significance level? So to answer that question, we first want to set up the hypothesis. Again, we put the part that we're arguing for, that we're hoping the data will support, into the alternative. So we're showing, we're taking the side of the alternative and trying to let the data be the judge. This is a right tail test, so all the alpha risk of the type 1 error is going to go on the right tail of the distribution. And here, because it's a mean of a small sample, we're going to use the student's t-distribution. And like I told you before, we need that degrees of freedom. So here we're going to calculate the test statistic for this population, test statistic for the population mean. And so remember, the mu naught is the hypothesized value of the population mean. The degrees of freedom is n-1. And so putting all that together, we find that for a sample of 25, the degrees of freedom is 24. So our sample had 71 as the average age of retirement. And so we're going to calculate this t statistic on 24 degrees of freedom, and it comes out to 2.22. Now, to find the probability of that, we're going to go to R, because we need to determine the probability associated with a t, a random variable that has a student's t distribution. So to do that, to find the probability that some random variable that has a designated degrees of freedom is less than or equal to some number, we're going to use PT, just like P norm. So this is PT, and we're going to put the quantile in. So this is where we're going to put our t statistic, the degrees of freedom, and the default is lower tail equals true. So if we want to use the right-hand side of the distribution, we need to put lower tail equals false. So for us, we want to calculate the p-value when the sample mean is greater than or equal to 71, and this is associated with the probability of a student's t-distributed random variable with 24 degrees of freedom being greater than or equal to 2.22. And so we put this into R as PT on 2.22 with the degrees of freedom equals to 24 and lower tail equals false. And again, the reason for that is because we have this greater than or equal to, and that is a huge arrow. Let me see if I can make it smaller. Okay. Okay, so because it's greater than or equal to, we're going to put that lower tail equal to false, and what we get out of that is a 0.01806. So the next step after we get the p-value is we have to make our decision. So if H naught were true, if the null hypothesis were true and the mean age of retirement really was at 67 years old, there's only a 1.8% probability that the sample would have a mean of 71 or greater. Since we set our alpha at 5% and the p-value is less, right? So 0.01806 is less than the 0.05. The test is significant, which means that we reject the null hypothesis and accept the alternative hypothesis that the mean retirement age is greater than 67. We're not saying how much greater, we're just saying it is definitely greater than 67. So again, we're looking at the p-value is the probability at the tail end of the distribution, and we convert over to the student's t to accurately determine what that probability is. And because it is less probability than our alpha, our risk of a type 1 error, we feel confident that, or we can say that it's statistically significantly different. Okay. Decision rules based on p-values. You can reject the null hypothesis if the p-value is less than alpha, and we say it's statistically significant, or you do not reject the null hypothesis if the p-value is greater than or equal to alpha, in which case we say it's not statistically significant. It's important to set the alpha before you see the data to avoid bias. So most hypothesis tests are conducted using a significance level of 1%, 5%, or 10%, using alpha equals 0.01, 0.05, or 0.1 respectively. In the previous example, the p-value was 1.8%, so we rejected the null hypothesis at a significance level of 5%. But if it had been 1%, we could not have rejected it because 1% is smaller than 1.8%. Depending on how the hypothesis tests are set up, the following table holds. If your alternative hypothesis is that the population mean is greater than some value, use the right tail probability. If it's that the mean is less than some value, it's the left tail probability, and that if it's not equal to some value, we have the two tail probability. And you can either multiply the probability by 2 and address the significance that you were asked for in the problem, or you can do it the way I did in a few slides ago, where I showed you dividing the alpha in half and putting it on each tail and then comparing the probability you have in the tail to alpha over 2. I believe that that is more consistent overall with the different methods, and it's more visually clear what we're doing. But you can do it the other way as shown in this table if that's how you prefer for some reason. Okay, so here's another example. And here, this is a single mean small sample, and we're going to talk about the student's t distribution. So here, the dean at a large university in California wonders if students at her university study less than the 1961 national average of 24 hours per week. You may remember this was the very initial problem we started out with. So she randomly selects 28 students and asks their average study time per week in hours. From their responses, she calculates a sample mean of 16.3714 and has a sample, there's a sample standard deviation of 7.2155 hours. So in order to answer the question, the first thing is we have to specify the competing hypotheses to test the dean's concern. And then calculate the test statistic, then find the p-value, then make the decision, or see what the data, we can conclude using the data. So, and we're going to summarize it, of course, in the end. So we'll start out by stating the hypothesis. And so we have that what the dean is trying to determine, so we put that in the alternative, is if the mean of her students is less than the 24 hours that was found in the 60s, whenever that was. I think it was 61 or something. So we put the alternative is the opposite of that. So if the mean is less than 24, the alternative, which has to be the complement, is greater than or equal to 24. So notice that this, we're talking about the mean being less than the expected value. So the test is left-tailed, so all the alpha is going to go in the lower tail. We're going to calculate the test statistic with the degrees of freedom of 28 minus 1, which is 27. And we're going to put this into our test statistic formula for a t distribution. So we use the same thing we do for the standard normal. The only difference here is that we have this little 27 here indicating that when we go to get any kind of probability with this quantile, we have to remember there's 27 degrees of freedom and it's coming from a t-distribution. So when we do this calculation, we see that we get a negative 5.594. And again, we're going to go to the left side of the probability distribution. We see that because we see the negative here. And we also saw it that it was a left tail test up in the alternative, the way we set that up. So now we're going to get the p-value using this t statistic from the t-distribution, the student's t-distribution. So to get that, so in statistical mathematical terms is what we want. And then in R, we put it into the function PT, and we put in the quantile. So the probability under the curve from negative infinity all the way up to negative 5.594. And then we have a degree of freedom of 27. So we put that in, we get this really, really small number. So it's 3.1 times 10 to the minus 1, 2, 3, 4, 5, 6. So 3.1 times 10 to the minus 6. Very small number. And then from this, we can decide, we make the decision and we say, okay, well, this test is statistically significant. In other words, we're going to reject the null hypothesis and accept the alternative because the p-value is less than alpha, the alpha, which was 0.05. And in summary, at the 5% significance level, we conclude that the average study at the university is less than the 1961 average of the 24 hours per week. All right, so now let's go to the last of these three types that all fit this pattern, where we're talking about a hypothesis test on a proportion. This example says a statistician read that at least 77% of the population oppose a $1 bills being replaced with $1 coins. To see if this claim is valid, the statistician selected a sample of 80 people and found that 55 were opposed to replacing the $1 bills. At an alpha of 1%, can it be concluded that less than 77% of the population are opposed to the change? So the first thing is we're going to set up this hypothesis. So we're going to see if the data can support our alternative, which is asking, is the actual population proportion that is against switching from bills to coins less than 77%, or the null, which is that it is actually greater than or equal to 77%. This is a left tail test, so all the alpha is at the left tail of the distribution. We're going to calculate the test statistic, so we take our sample proportion, which is 55 over 80, and we get 0.6875. And from this, we're going to calculate the standard z-score. Remember that the standard error is a little different for proportions. And it's the same as we were working with in section 5.2. It's going to be the sample proportion times 1 minus the sample proportion divided by the sample size. And here we see that we get a z-score of negative 1.592. And from this, we're going to calculate the associated p-value. And we're going to do this from the standard normal. So we just use in R the function p-norm. We put in our quantile of negative 1.592. We don't need to put anything about the mean or standard deviation because the default is that it's the standard normal with a mean of 0 and a standard deviation of 1. We don't need to say anything about the lower tail because the default is that it is lower tail equals true. So it is going to, by default, give us the lower or left tail. And we get out of this a value of a probability of seeing this result if the null was true of 0.056. So the decision is, since this p-value is greater than 0.05, we cannot reject the null hypothesis. And we would say that this test is not significant. It's showing that the proportion of the population opposed to replacing $1 bills with coins is less than 77%. Okay. And that will conclude the rest of what is covered in Chapter 5 in the Connect course. Next week, we're going to be learning about how to do hypothesis testing under those different tests that I was talking about. so that you can actually do something useful with hypothesis testing. Okay, thank you and have a great weekend.